Welcome, students! In our previous classes, we've spent a good amount of time learning how to draw ray diagrams to figure out where an image is formed by spherical mirrors. Today, we're going to move from just drawing to actually using formulas. This is going to help us find those exact, precise answers we need for our exams.
So let's start with a simple question. We know how to draw ray diagrams to locate an image, but think about it. Are they really accurate enough when it comes to numerical problems, where every decimal point matters? Are they enough for precise answers?
You see, while ray diagrams are fantastic for getting a visual idea of where the image is going to be, they are, at the end of the day, approximate. For exact calculations, we absolutely need formulas. Formulas give us the precise position, the exact nature, and the correct size of the image, which is so important for solving numericals correctly.
Now, before we even touch the formula, we must first learn the language of mirrors. This means we have to understand the key terms and, most importantly, the rules of the sign convention. Getting this part right is the very first step to solving any problem correctly.
Okay, so let's look at the three fundamental quantities we'll be working with. First, we have the object distance, which we represent with the letter U. This is just the distance of the object from the pole of the mirror. Second is the image distance, V, which is the distance of the image from the pole. And third, we have the focal length, F, which is the distance of the principal focus from the pole. So remember these three letters, U, V, and F.
To use our formulas correctly, we need a consistent set of rules for all the signs, positive or negative. This is called the new Cartesian sign convention. Basically, we treat the pole of the mirror, that point P, just like the origin on a graph. And the principal axis becomes our x-axis. This system makes all the rules for signs very clear and easy to follow.
Now, these four rules are very, very important. You have to memorize them. Let's go through them slowly. 1. The object is always placed to the left of the mirror. Always. 2. All distances, no matter what, are measured from the pole. 3. Distances to the left of the pole are negative and to the right are positive. And 4. Heights above the principal axis are positive and heights below are negative. And just think about it. Since the object is always on the left, what does that mean for the object distance U? It means U will almost always be negative.
All right, now that we understand the sign convention, we are finally ready for the formula itself. This is the key relationship that connects the object distance, the image distance, and the focal length all together.
And here it is, 1 upon V plus 1 upon U equals 1 upon F. This is the famous mirror formula. It's a really powerful tool because it works for both concave mirrors and convex mirrors, and it doesn't matter where you place the object. But you must remember, it will only give you the correct answer if you apply the sign conventions properly when you substitute the values.
Just knowing the position of the image is not enough to get full marks on a problem. We also need to know its size compared to the object and whether it's upright or inverted. For this, we use a concept called magnification.
So, magnification, which we represent with the letter M, simply tells us how much larger or smaller the image is when compared to the object. It's just a simple ratio, the height of the image, which we call h dash, divided by the height of the object, h.
Now there's also a second way to calculate magnification, which is incredibly useful. We can find m by using the image and object distances with this formula. M equals minus v upon u. Please pay very close attention to that negative sign in the formula. It's not a mistake. It is a very important clue that helps us figure out the nature of the image.
You know, the best way to learn all this is by actually doing it. So let's solve a couple of typical exam problems together. We'll do one for a concave mirror and then one for a convex mirror to see how it all works.
First up, let's tackle a problem with a concave mirror. So, an object 4.0 centimeters in size is placed at 25.0 centimeters in front of a concave mirror that has a focal length of 15.0 centimeters. Our job is to find the position, the nature, and the size of the image. Let's do this step by step.
Okay, the first and most crucial step in any numerical is to list down all the given quantities with their correct signs. So the object height h is placed upright above the axis, so it's plus 4.0 centimeters. The object distance, u, is on the left, so it's minus 25.0 centimeters. And for a concave mirror, the focus is also on the left, so the focal length f is minus 15.0 centimeters.
Now we just use the mirror formula. We'll rearrange it to find 1 upon v. Then we substitute the values of f and u very carefully, making sure we include their signs. So 1 upon v equals 1 upon minus 15 minus 1 upon minus 25. A little bit of calculation, and we get our answer for V, minus 37.5 centimeters.
Great, but we're not done yet. We still need to find the size of the image. For that, we use the magnification formula. Let's just rearrange it to solve for h dash. And again, we substitute all the values we know with their correct signs, u, v, and h. After the calculation, we find that h dash is equal to minus 6.0 centimeters.
So, what do all these numbers actually tell us? Well, the image distance v is minus 37.5 centimeters. That negative sign tells us the image is on the left side in front of the mirror. This means it is a real image. So you need to place a screen at 37.5 centimeters to see it. Next, the negative sign for h dash tells us the image is below the principal axis, which means it is inverted. And finally, since 6 centimeters is greater than 4 centimeters, the image is enlarged.
Excellent. Now let's solve a problem for a convex mirror. This is the kind you often see on vehicles as rear-view mirrors. So a bus is 5 meters away from a convex mirror, and this mirror has a radius of curvature of 3 meters. We need to find the position and nature of the image.
Okay, first step, as always, list the data with the correct signs. The object distance u is on the left, so it's minus 5.00 meters. Now the radius of curvature r is 3.00 meters. For a convex mirror, remember the center of curvature is behind the mirror, on the right side. So r is positive. This means the focal length f, which is just half of r, is also positive, plus 1.50 meters.
We follow the exact same procedure. We take our mirror formula, 1 upon v equals 1 upon f minus 1 upon u. We substitute our values, being very careful with the signs. After the calculation, we find that the image distance v is positive 1.15 meters.
Now let's interpret this result. The image distance v is positive. What does a positive v tell us? It means the image is formed on the right side behind the mirror. This means the image is virtual. Now let's calculate the magnification, using m equals minus v upon u. This gives us a positive 0.23. The positive sign for magnification confirms the image is erect, and since the value 0.23 is less than 1, the image is diminished, which means it's smaller than the object.
We've now solved 2 different problems and interpreted all the signs. To make this even easier for you in the future, let's put everything we've learned into one simple table. You can use this as a quick reference guide for any problem you face.
This table right here is the key takeaway from today's entire lesson. If v is positive, the image is virtual. If v is negative, the image is real. It's that simple. If magnification m is positive, the image is virtual and erect. If m is negative, it's real and inverted. And if the value of m is greater than 1, it's enlarged. If it's less than 1, it's diminished. If you truly understand these rules, you can perfectly describe any image.
And to end, here's a little something for you to think about. If a mirror produces a magnification of -1, what can you conclude about the image and the object's position without doing any calculation at all? What does that negative sign tell you, and what does the number 1 tell you about the size? Think about it. Keep revising these concepts, and you will surely master this topic.